Hello and welcome back. In this video we'll be working through an example where we'll find the curvature of a parabola. So here we're given a vector equation for a parabola. Notice we have a parameter here a that can be changed, and so we're really considering lots of different parabolas that are all centered, not centered, but have vertex at the origin. So changing A is going to end up with a different type of parabola. One thing we might do first is just recognize what this looks like just sort of in normal, for a scalar valued function. So that is y in terms of x. Notice that here y, my y component, is a times x squared. So this is the parabola that we're looking at if we think of this just sort of graph normally, not as a vector function. So it certainly is a parabola, and let's go ahead and compute its curvature function. So remember, this is a commonly forgotten thing, that the curvature is not just a single value, not necessarily a single value for the curve, right? The curvature changes depending on where I am at the curve. So when we say compute the curvature, we're talking about a curvature function for the parabola. Input a point on the parabola and come out with the curvature at that point. So let's go ahead and start with how are we going to actually compute this curvature. In the last video, we came up with this nifty formula for curvature. I'd like to use this if we can, just so we can practice using it. And let's briefly remember the assumptions for that. What do we need in order for that formula to make sense and work? Well, we need the velocity to never be zero and the acceleration to never be zero. So we're going to want to check for that. If that doesn't work, we'll have to go back to the other curvature formula, which remember was 1 over magnitude v times magnitude of dt. So let's go ahead and start by just computing velocity and acceleration. So velocity looks like 1, 2, at. Notice that the x component of this is always 1, and so the velocity vector is never the 0 vector. So just take note that this is not the 0 vector for any value of t. Acceleration, when we differentiate with respect to t here, we get a 0, so we're in danger of having the 0 vector as an output for some value of t. But when we differentiate this, we get 2a. So as long as a is not 0, we are fine, where a is a real number. So if we just say a not equal to 0, let's go ahead and add that to this. Let's assume a is not equal to 0. Then acceleration will never be the vector 0. And these are both for any t. It's never the 0. And that's what we want to be able to use our new fancy curvature formula that looks like magnitude of v cross a over magnitude of v cubed. So why don't we go ahead and compute now. How about we're going to need magnitude of v at some point, right? Why not just do that now? Let's do magnitude of v. And of course, there's different orders you could do this. You could start by doing v cross a. That's fine. I'm just going to do v first. So magnitude of v is going to be square root of 1 plus 4a squared t squared. Magnitude of v. And then let's get a hold of v cross a. So v cross a, remember how to compute cross products. A nice way is to use that determinant formula. And then we'll have to remember for a second, so let's maybe start setting up. This is the determinant of a matrix, right? It goes I, j, k. And then I put the vectors in, right? Velocity, I'm doing v cross a, so I'll do velocity and acceleration. So I go 1, 2, at. And then what do I put for the k component here, right? This way of computing cross products only works in 3 dimensions. Do you remember what to do if we're just in 2 dimensions, if we don't have a third component? We just let it be 0. Remember that a 2-dimensional vector really is also a 3-dimensional vector. We can embed the 2-dimensional space, the xy plane, inside of 3 space. One way to do this is just setting the z component to 0. So we just set that equal to 0. It's our way of skirting that issue. 0 to a, and 0. So let's find the determinant of this. It's been, a minute since we've done a problem like this. So let's go ahead and remind ourselves how to do this. I'm going to expand along the first row. So I times determinant of this. Notice I'll get 0 here. So that's 0i. How many j's? Well, if I do the j, I'm also going to get a 0 because these are all. Okay, and this should make sense, right? If I take two vectors in the xy plane, remember that the cross product of those two vectors is orthogonal to both. Hence, if those two vectors are not parallel and they're in the xy plane, a vector orthogonal to both will be orthogonal to the xy plane. So it shouldn't have an x component and shouldn't have a y component. And we're seeing that here when we compute the determinant. And finally, k is where we'll actually have a non-zero quantity. So for k, we have 2a minus 2at. So I'll say plus 2a minus 2at. And that's k. And we need the magnitude of that. So we have v cross a. Let's compute magnitude v cross a. Well, it's just got one component, so this is square root of 2a minus 2at. Let me maybe clean that up a little bit. So this looks like 0, 0. We can pull a 2a out of this. So this is 2a times 1 minus t. And so when I square that, it's going to look like 4. Right, we're squaring the whole thing, and then we're taking a square root. So we should just get out. Let me actually just go through it, but we should just get out the thing because we didn't have any other components. 1 minus t squared. Right, so when we take a square root of that, we end up with 2a. Maybe we need to be a little bit careful there. Here, a is a real number, so we should actually get 2 times absolute value of a there. And then here we have 1 minus t squared, square root of that. So that's a absolute value of 1 minus t. Remember, t can be bigger than 1, so that's possible. That's negative. So maybe it's good we ran through that because we also have absolute values going on here. All right, so remember that curvature. So now we have all of our pieces. Remember, this is how I recommend to do things. Get all your pieces together, your mise en place, and then compute. So curvature is magnitude v cross a over magnitude v cubed. So magnitude v was this. That means magnitude v cubed will be 1 plus 4a squared t squared. That's to the 1/2, so this will be to the 3/2. So what we have here then is 2a 1 minus t all over 1 plus 4a squared t squared to the 3/2. Now I knew something looked funny when I was computing this, and I don't like to, if I make a mistake somewhere in the calculation, I don't like to just stop the video and remake it. 1, because that takes extra time, and 2, because we lose a valuable teaching opportunity. Did anyone spot my mistake when I made this? I'll tell you that the mistake was made when I was computing v cross a. Did anyone catch it? If you didn't catch it the first time around, like I didn't, here's your chance to try and find it. Go ahead and pause the video and see if you can find the mistake that I made. It was right here when I computed, v cross a. I did 2a minus 2at, but 2at was being multiplied by 0, right? 1 times 2a minus 2at times 0. So that 2at should not be there. So this is, again, what I recommend doing is doing everything in pieces like this, because now it's really easy to kind of correct my mistake. So this isn't 2a times 1 minus t. It's a lot simpler than that. It's just 2a. And that means my magnitude then should just be 2a. Or rather, 2 times absolute value of a. And then we can go back and correct this. So instead of 2a times 1 minus t up here, I just have 2a over this. We just consider positive values of a. We'll be fine. We don't need this absolute value. But if we want negative values, if we want to consider a parabola facing downward, we're going to want an absolute value here, right? Curvature should always be a positive quantity. Okay, or at least non-negative, rather, because a line has zero curvature. Okay, cool. So here's the curvature of a parabola. Notice it's a function of t. So in order to get the curvature at a point, right, notice this is a function of t. In order to get the curvature at a point on the curve, I need to know at which point, at which time t we're at that point on the curve. So if I want it, say, at the vertex of this parabola, that occurs when t is equal to 0, because then I'll be at 0, 0, and I know that's my vertex. So like, for instance, k of 0, what's my curvature at the vertex? And if we think about a parabola, right, thinking about a parabola, we should have the highest amount of curvature at the vertex, right? At least that's our guess, that's our hypothesis, and we can test that. But let's go ahead and compute the curvature first, and then we're going to look at this function for a bunch of different values of t. So k of 0, so put 0 in for t. I'll just get 1 on the bottom here. I'll just get 2a. So if I'm just looking at y equals x squared, my curvature at the vertex would be 2. All right, I'm going to jump to an interactive figure from our text. I'm trying to remember what scene I have this in. Let's try this. Yep, there. Here is my parabola, right? I just put in t, at squared. So it knows this is a vector valued function, and it's going to graph the trajectory of it. And then a here, I can wiggle around a. So when I use in GeoGebra, when I put a parameter a in this, it knows, it recognizes that as this variable quantity that I can then change. So we can change this. Maybe I'll start with just 1, a equal to 1. So we just get the parabola y equals x squared. And alongside this, I'm going to plot the curvature function. And that's just in blue here. So notice how the curvature goes along with the curve itself. And you might have had some hypotheses here that as we sort of go t negative, as we look at t goes to negative infinity, this approaches the shape of a line. A line we know has 0 curvature. And so we should see the curvature going to 0 as t goes to a negative infinity, and similarly as t goes to positive infinity. Again, we approach a linear function, and so our curvature goes to 0 as well. And then the curvature should peak here at the vertex, and we can see that in the curvature function, right? As t is at 0, our curvature is 2. And that's what we predicted, that's what we just calculated. Right, so there's our maximum curvature. The curvature increases continuously until we get to that point and then decreases past that. Let's see how we change when we change a. How does the curvature change? So this is higher values of a now, which is going to correspond to a steeper parabola, right? That should affect the derivative and make it a lot higher. So as I increase a, notice this peak is happening here when I put t equals 0 in. We should always end up with 2a. So this peak is exactly twice a all the time. And so there's how the curvature changes of a parabola. I can consider negative values, but this is incorrect, right? If my parabola is going down like this, I shouldn't get negative curvature. Curvature should never be negative. So I made a mistake here when I was actually inputting my curvature function. I didn't use absolute value of a. I just used a. And when we did those calculations, right, we had square root of a squared, and that's absolute value of a. So the way to fix that then is to just make sure we have absolute value of a there. And now our curvature should make sense for parabola pointing downward like this. And so again, as I make it more and more negative, we should get more and more curvature there at the peak, but we still have this property that as t goes to infinity or negative infinity, the curvature goes to 0. What happens if I do a equals 0? Let's see, will it even let me? Let's see if I can just plug in 0 for this. Right, we had to not do this, right? Remember early on in the calculation I had to say let's not let a equal 0 because that threw things off, that let the acceleration be 0. And that means our vector valued function would just be t0, which isn't going to do much for us. So we'll just toss 0 out. It's not a parabola at that point. All right, that is it for this video. In the next video, we'll be computing the curvature of a helix. So that'll be pretty exciting. Hope to see you there.